Okay. So I'm going to apologize to the camera person because I don't like standing behind these. I feel like I just kind of hide and I can't really see the people over there. I do want to be able to see my slides without looking backwards. All right. As Julia said, my name is Juliet Hougland, and I'm a data platform engineer at Stitch Fix. I'll be talking about Apache Spark and real production machine learning workflows, how the two can fit together. The reason that I'm here today is because I used to work at Cloudera, and I've given a lot of talks about Spark. So the organizers reached out to me, and they were like, hey, Juliet, we've seen your talks. Please, come to Zurich, have a great time in the fall. And I said, yes, give me all the chocolate. I'm very excited. And that's actually worked out great. They took us on a little tour of a chocolate factory. And while I was at Cloudera, I actually had two different roles. I both worked with our customers originally and did a lot of community outreach where I started giving talks, worked with our really big customers, advised them about how to use Spark and how to use Spark in real production applications, how to get their data scientists to use different big data functionality and tools that we provided. And then I started leading data science inside of engineering at Cloudera. I switched jobs maybe 3 weeks ago. So when I showed up, I was like, oh, hey guys. Just wanted to let you know, at a new place now. And I didn't actually really think about this, but I realized as I came on stage and saw my picture there and the Stitch Fix logo there that I've really coordinated extremely well. So I'm very proud of that. Hopefully you're excited about my slightly more specific talk than originally advertised. I think when I was asked to come give a talk here, I was like, oh yeah, sure, I'll talk about Spark and big data or something. And so my title was pretty much Spark and Big Data or something, and my abstract was I'll talk about Big Data and Spark. I tend to leave things a little bit loose because I like to entertain myself, and this talk is very entertaining to me. So we'll see what you all think about it, but I'm pretty amused. So the first thing that I want to get across is that Spark is an ecosystem. As you probably picked up from Romeo's talk, there are a number of pieces that go into the Apache Spark ecosystem. As a project, it's huge. If you ever want to heat your house, you can try compiling Spark from source. Your fan and your computer will start going. You won't need to start a fire. It's pretty fantastic and amazing. So there's a few different components that fit into Spark, and I wanted to go over those so I can describe how that actually maps on to real production machine learning workflows. At the core, there's Spark Core, which Romeo described. You have these, you have this RDD construct, and Spark as a framework takes care of farming out work to different executors in your cluster. But you tend to not work directly with RDDs. In general, you're encouraged to go through a data frame API, and in Spark 2.0, the focus has shifted to either data sets or data frames, depending on what language you're accessing Spark from. So this data frame API is extremely useful and powerful because it allows the different components of Spark, like Spark SQL, which allows you to write things like SQL statements and have typed tabular data in sort of an accessible way, and also to allow Spark MLlib to stitch together pieces of a pipeline and have them point at different columns. And the reason that these two things come to mind for me is that they're the ones that I tend to use the most. I tend to be able to want to access tables or access tabular data in some way via Spark, and then I also want to build machine learning models. The part that I'm eliding here and leaving off is the different language capabilities. So again, as Romeo said, I'm really actually so happy that he gave a nice overview of Spark because I'm going to skip through this pretty fast. The languages provided for Spark are Java and Scala, Scala being the primary core language that Spark Core itself is written in. And Scala really is the first-class citizen. If you're going to write anything in Spark and you want it to be simple, straightforward, completely understandable, Scala is the way to go. Java is equally easy, if a little slightly clunkier. If you get into Python or R, the support of it decreases, where Python tends to lag behind a few releases in terms of functionality that is actually in the Python API. Python tends to lag behind a few releases, whereas the R functionality that's built into Spark itself is relatively poorly supported, and most people agree you probably shouldn't use it. The people that use and make RStudio have actually come out with their own package called Sparkly R, which is significantly better supported, a lot more natural for people who already write R, and so that's worth exploring. And all of the examples that I'm going to use today are going to be in Python. And so 2 reasons. One, Python code, it looks really nice on a screen, and it's kind of short and condensed. And the second is that a lot of normal machine learning workflows happen in Python. A lot of data scientists already know how to use Python. They have libraries that exist. They can write reasonable data cleanup sort of ETL code, and then also have their machine learning model pipelines implemented in Python. And so transitioning from Scikit-Learn to using PySpark is a pretty natural transition. And so Spark is the distributed computational framework, and you're going to be computing on something. Frequently, people think of Spark as interacting with incredibly large data sets. So something that would actually drive using Spark, kind of like one of the last questions from Romeo's talk pointed out was, if you can use Spark on a single machine to do the same thing, why would you do it? The answer is you probably wouldn't. You would really get driven to using distributed computational frameworks because you have a distributed computational problem. And frequently, that distributed computational problem is that you have a huge data set that is inside of HDFS or inside of S3, or is a big Cassandra table. And what you then need to do is do some processing on it. But I will talk in greater detail about different types of distributed computational problems. Oh. Okay. So, typical hardware. This I kind of want to use to motivate what I mean when I talk about these distributed computational problems and what might bring you there. So who here, there's been a lot of quizzes today with hands raising, I really like it. Who here has been inside of a data center? That's awesome. I have worked with huge clusters of computers for about 5 years now. So prior to Cloudera, I worked at some startups that were big data startups. They're now pretty much defunct and almost dead. But in my 5 or 6 years of big data experience, I've never physically gone to a data center. But I know a lot about rack-mounted servers, since we have a picture of a rack-mounted server. And what you'll see is that there's always LED lights, so you know that they're working. And they're networked together using some Ethernet, great. But really what's going on in these, or the way that I think about these conceptually, is that each of these have a certain amount of storage and compute resources. And so this is the traditional in-house data center configuration, where you literally have a rack of networked together servers. Each of them has storage, as in hard drives, and then compute resources, as in CPUs and RAM. And these are networked together in such a way that they can talk. And then the way that Spark ends up interacting with them is that there's the distributed storage sections. This might be something like Cassandra, HDFS, some sort of way of putting a file system over all of this network storage. And then also the distributed computation part, which is basically, okay, we know that we have all of these compute resources. We have a bunch of processors on each of these servers. We have RAM on each of these servers. We're going to use the fact that they're networked together to farm out our computation. And so when it comes to writing a Spark program, what you do as a user is you write a driver program. And you say, hey, Spark, I need you to create this data set, this like RDD, this data frame, whatever abstraction you're using, and then maybe map over it and do these sort of computational things, maybe shuffle it around by these keys, and then write something out to a file. And you write that in your driver program, which happens on this edge node. And so this edge node has also storage and compute because it's a computer. But there tend to be significantly more compute resources than storage resources on these. And this is also networked into your cluster. So this has some way of talking to the rest of the rack-mounted servers and saying, and orchestrating work with them. And so Spark itself is a framework that takes your driver code on your edge node, executes it, and knows how to communicate with all of these servers that are actually living in your data center. Romeo pointed out that a new trend in configurations of clusters like this is decoupling of storage and compute. And so you can imagine that instead of thinking of all of our storage being on the same servers as our compute, that what we might have is a bunch of data in S3, and then we're going to bring up a cluster to compute on some of that data. So that's interesting, but I think the fun meat of this is, okay, we have some sense of how Spark works. You write a driver program, you execute it on an edge node, and then it farms out work to all of these networked together computers that are in some data center somewhere, maybe in the cloud, maybe in your own servers. Well, what does this mean for data scientists, right? I'm pretty interested in that relationship between a data scientist's actual work and then the tools that we provide them. And so when I was working at Cloudera, I thought it was really fascinating to think about ways in which distributed computation is actually practical and useful. I think I joined Cloudera at this peak of the hype cycle, right, where everyone's like, oh yeah, big data is going to solve all of your problems. You just throw some, at the time maybe MapReduce on it. Then Spark came around, it's like, yeah, just use some MapReduce, use some Spark, this will just fix everything. And if that is the attitude and impression that you come to distributed computational problems with, you're going to be buried underneath a pile of stack traces and log files on all of these servers. And you're like, why am I here? How did I get here? What sort of choices have I made in my life that brought me to this place? And that's a good question to be asking. So let's think about what it means for a data scientist to actually build a model and how Spark might fit in there. So at a very high-level view, we have what I like to think of as the modeling lifecycle, the machine learner's workflow, where we have a bunch of historic data in a database somewhere. We then are going to train our model, which I describe in this very simple box. It's like a little square. It says model training. It's actually a pretty complex process, and I'll go into more detail about what that is. But a data scientist trains a model. You have a persisted, finalized model that you then want to deploy, and you want to deploy that to new data. So the whole point of machine learning is you look at some old historic data, you build something useful that generalizes to new data that comes in, and then you want to apply your model and get some sort of useful results. So this could be fraud detection, where you have old credit card transactions. You create a fraud detection model, you deploy this into your credit card system or your credit card transaction processing system, and then on the fly determine, is this new transaction fraudulent or not? That deployment step is actually pretty complex, and the model training step, similarly complex. So how does Spark actually fit into a normal machine learning modeling lifecycle? Or how can it? And why would you want to use it? Other than wanting to be at the peak of a hype wave, right? I've been talking really general, big, vague generalities, and that gets kind of hard and has me talking in circles pretty quickly. So I want to take a concrete example and actually use that to describe in greater detail and show you some code examples of the different ways that a machine learning workflow might look for a specific example. So I want to use customer churn. And I'm using customer churn because it is a simple model where you basically have supervised classification. You have a supervised problem, you're doing classification of, you have a bunch of customers in your history and you want to say, are they going to be your customer next month or not? So it's simple to describe, that's nice. It's also incredibly practical, and I've implemented production machine learning workflows on customer churn a few times with Cloudera's customers in Spark. And so I feel like I have some sort of sense of what happens here. So with customer churn, we can say that we're, a telephone company, and what we're interested in is knowing of the customers that are currently our customers, who's not going to be a customer next month, who's going to churn. Well, any good example needs real data, and real data is actually very, very easy to find, particularly at the UCI machine learning library. There's the link to where I found this at the top, and this, I think, is just called telco churn dataset. So what we have is essentially a big CSV file that we download, and inside of there, it's a text file, it's a CSV, which is not the best sort of file format to be using in general, but sure, little example, easy to view. We have information about each customer on a line. So one customer at a point in time is a line in this text file. And the very last column is a true or false, which says whether or not this customer churned. Let me think about this. Whether or not this customer churned. So true means next month they were not a customer. And then every other column is just information about them. So some of these are discrete features. So this is a US customer base. We have like what state they live in. We have the phone numbers. We have how many international minutes were used, how many nighttime minutes were used, how many off-peak minutes were used, how many times they called customer service in the last 3 months. It doesn't really matter what columns I'm going to use here. But one thing I do want to point out is that we have this raw data set. And some of these features that we're going to use in our machine learning model are not yet numbers. They're discrete, right? And so beyond discrete, they're categorical. So the US has 50 states, 4 territories. We need to transform this string into something that an algorithm can actually learn on, so meaning a numeric value. And so this immediately implies that we're going to have a pipeline. We can't just take this, a CSV line, and say, okay, here's the thing we need to train on. We actually need to transform every individual or entity that we're trying to train or do predictions on, meaning every customer, into a feature vector that our model can understand. And so for most of these discrete variables, what we're going to end up doing is one hot encoding, which you basically take the same number of categories, maybe the number of categories minus 1, depending on how you want to do it. You make a vector that is the number of categories you have, and you have a yes or no Boolean saying it is that category or not. And so I'm wearing a patterned shirt. Michael is not wearing a patterned shirt. I could have a feature vector that has 2 components, one for patterned shirt, one for not patterned shirt. Mine would have a 1 in the patterned shirt and a 0 in the not patterned shirt component. So that's a step that we need to take before we actually apply a model. And that's part of this model training workflow. And so what we're doing is we're taking training data. We're going to transform this training data with featureization. So some of this is just taking discrete or categorical variables and turning that into something useful. Some of it might be doing PCA to reduce the collinearity of features that we have together. Can be doing any number of things, but making our features into more useful features for our model to train on, and then actually fitting a model. So we might have something like logistic regression for this churn prediction, or we could have something like a gradient boosted machine for classification, any number of classification algorithms, and we want to be able to swap these out relatively easily. And so different libraries have developed useful abstractions for making pipelines or composing these steps together of featureization and model training. And that is what I think of as the model training pipeline, to go from data to a persisted model. Like, we fit this model, we're going to write it out somewhere, and then we can actually do something useful with it. That useful thing, when we're still in the model training phase, could be evaluation of this model. So I think if you were here for Paige's talk this morning, that she pointed out that often you'll take a data set and do 70, 15, 15, where you take out 15%, and you're like, okay, I'm not going to look at that until I'm done. And when I'm done, I'm going to take my final model and see how it performed. And before then, you're going to do cross-validation with that 70 and other 15%. So this is the general workflow and the way that you split up your data, the models that you produce. What does this look like in actual code? Well, if you look at Scikit-Learn, which is the prototypical sort of father of all abstractions for data science pipelines, you'd see that what they have is generally a model that you train on training sets, both for your predictor variable, or your predictor is the thing you're trying to predict, which you usually call y, and your prediction, or your features, are usually x. And we've split that into 20% of it goes into the test set, whereas 80% goes into the training set. And then on that training set, the x and the y, we fit this gradient boosted regression model, and we predict what it is on that held out set. Okay, this is great. We have some amount of work that had to happen, and we can see that actually back here, if the get data knew how to do the proper data processing to go from those CSV lines to actual feature vectors, we would be done. But we actually want to be able to apply the same pipeline to new data coming in. So if new data comes in and it needs the same feature transformations, we need to actually store that and hold that with our model, right? So Scikit-Learn has the concept of a pipeline. And you can explicitly say, hey, Scikit-Learn, I have multiple steps that I need to do when I am applying my model to data, whether that's during training or during model application. And this is the order that the steps need to happen. So in this case, we have a one-hot encoder on categorical features. So I believe here I'm using the 0th column, which is that state column, and the 20th column, which is that predictor column, the true or false. And then there's actually a classifier that I'm going to use. So this pipeline describes how this model performs in training and in evaluation stages. And then the code looks exactly the same, except we've replaced the model, the gradient boosted machine model, with this pipeline object. And the reason we can do that is that machine learning models in Scikit-Learn are pipelines by themselves, but you can also compose them with other transformation steps to make more pipelines. And so the API calls all look the same. Great. Now, the reason that I said that Scikit-Learn is sort of the prototypical pipeline is that Spark and Spark MLlib looked at their API and they realized that they needed to have the same sort of abstraction. And frequently, machine learning modeling libraries will realize relatively quickly in their development that they need this pipeline abstraction. And so MLlib has come up with this pipeline abstraction, and you'll get things like feature extractors, like this tokenizer that's on the board, or the hashing term frequency. This is an image that was pulled off the docs for the MLlib library. And let's say we're going to do the same, we're going to do pretty much the same steps, but with Spark. What this ends up looking like is actually, I think, slightly clearer. And you say, okay, I'm going to make this pipeline. The stages of the pipeline are put in order in a list where I'm going to turn this categorical feature into a vector with the indexers, the string indexer, which I believe is just a one-hot encoder, and then assemble multiple columns into a single vector. And so the assembler is required in Spark MLlib because Spark MLlib operates on data frames, and data frames are generally scalar values where you just have a single value in a column. And so when you say, hey, assembler, what I need you to do is make me a feature vector out of these 10 other columns and produce a feature vector in your output column, and then apply the classifier to that. And so in each of these, you're saying what your input and output columns are. And that's because, as mentioned, pretty much all of Spark SQL, Spark MLlib, Spark Streaming goes through the data frame API. And this is what I mean by goes through the data frame API for MLlib. So great. We know we have these pipelines, and that's how model training happens. Now we're going to deploy it. Super easy. And by easy, I mean not easy at all. Deployment is always the hardest part. Deployment means you have a production system and you've trained a model somewhere, and now you're going to actually move it over there. And so when I would work with customers and try to understand what people were having trouble with, most people could write a Spark job. Maybe they couldn't debug a Spark job, and they needed some help with that. But the hardest part was getting to the deployment step. So when you get to a stage in your machine learning model development, how are you going to deploy it? So I've been talking about these models that we've been building in Python. And in Python, we have a few options. The first option that jumps to everyone's mind is pickling. So who here uses Python frequently? Who here of you who uses pickle stuff? Great. So pickles are often very useful when used in a very specific targeted way as a long-term persistence method to transmit serialized objects between multiple Python processes over time, it is a terrifying thing to do, but it is an option. Pickles have a particular vulnerability around large-sized data objects, and often you do actually have quite a bit of data inside of a model that you've trained, and so that could be a lot of parameters that you fit. And so MLlib is meant to work around that and work around that sort of drawback of standard pickles. There's also a thing called PMML. PMML is the predictive modeling markup language. And some people recoil with horror because PMML is XML, but for describing machine learning models and machine learning model pipelines. I don't blame you. XML is not the easiest thing to read, but it is actually a pretty impressive system with a few open source projects around it. And it's what I'll talk about the most. And then the fourth option, which is also incredibly common, is having a custom deployment mechanism. And so sometimes that custom deployment mechanism is the data scientist turns to the systems engineer sitting next to her, and she says, hey, I have this model, will you implement it? The system engineer says, sure, describe to me how your model works. And she sits there and codes it up in C and deploys it out on their production server and production system somewhere. This is slow and error prone and kind of hard. There's other better custom deployment mechanisms, but kind of like Anna Karenina, each unhappy family is unhappy in its own way. I'm not going to go into the details of all of the ones that I've seen. I'm mostly going to focus on Pickle and PMML as two options. And when I say that, I'm really just going to first give you a reason that I'm not going to talk about Pickles or MLlib at all. So there's a few issues with Pickle and MLlib. I'd already mentioned that MLlib was created to work around this large data objects inside a Pickle issue. Outside of that, both of them have a few issues that should make you hesitant about using this for deploying saved models into production. The first is that they're insecure. If you were to unpickle some bytes that had instructions in it to go delete every file on your computer, it would just run happily if the process it was running in had the right permissions. And so you can have attacks on your own systems through pickled objects. So that's something you need to be aware of and cautious about if you choose to go the route of pickling. Second is it's not portable between different architectures and different systems. And so if you pickle an object in one place and then move it around and unpickle it somewhere else, if you have different system setups, it might not necessarily work. And for production deployment, that is likely a feature that you would want in your system. The third is that when you pickle these things, models themselves tend to be really big, and that means that these big things are also very slow. And this is kind of outside of the big data issue, but the pickled objects themselves are very large, and unpickling them then is very slow. So there's a few issues with this. I don't particularly recommend it. If you want to learn more about the issues with pickling, there's a really fun talk that was given at PyCon a few years ago that's called Pickles Are for Delis, which I think is just one of the best names for a talk I've ever heard. And it's pretty short, and I recommend watching it. It's just sort of interesting if you're into Python development. So instead, I'm going to talk about this beast of a system called PMML, which is XML for machine learning models. And PMML has a few different ways for you to use it from various systems, like if you're in Scikit-Learn or Spark. And so there are drawbacks to PMML. Not every model is fully supported in both the serialization part, where you take a model that you've trained and you try to write it. Depending on how you're writing it out, the model you've used may not be supported. Similarly, if you're trying to take a PMML file and then actually apply it, depending on the system you're using, it might not be supported. So do your research, figure out if being constrained to that selection of models is okay. But if it is, this is actually a very reasonable solution that has a few different products around it that allows you to actually use it pretty well. So in MLlib, they actually have functions that say to PMML on a model that you've already fit. And that will, and you pass it a path to a file, and it will then write out a PMML file to the path that you specify. This only has a few models supported, and there are other outside libraries that have been developed to just kind of get around this. You can do research on the internet for that. But there's many things that exist. And in Scikit-Learn, there's also a library called sklearn to PMML, which allows you to, similarly, to write out Scikit-Learn models that you've trained to PMML somewhere. Great. So you can at least serialize it into a file. In this built-in Spark PMML export, there's only a few models that are listed here, currently supported as of 2.2.1, I believe it is. So this is a good example of the sort of limitations that are inherent to using PMML for production deployment. But the cool thing is that you can also serve these back relatively easily, and I'll describe to you how that might work. So we now want to think about what it means to do distributed model fitting and how Spark actually fits into this workflow that I've described, where generally we have historic data, we do some model training, and I've shown you how to do model training using Scikit-Learn or using Spark MLlib, and that produces some sort of persisted model. And what I'm going to talk about now is what it means for that model training itself to be distributed. So I want to clarify the distinction between parallel and distributed. Parallel means it's happening in multiple, you're doing some sort of processing in multiple processes. Great. Distributed means those processes are split across many computers. So distributed model training means that model training is going to be happening across many computers, and there's only a single model being trained. And so the thing that is distributed here, so the pattern that I'm going to use in these slides is if I've highlighted it yellow, that is the thing that is distributed. Distributed model training, when there's only one model being trained, usually means that what we have is a huge input data set, and we're training a model, a single model, over that huge input data set. This is the classic thing that people should be thinking of when they're thinking of Spark, right? You have 10 terabytes of data. You want to train a machine learning model. It's not going to fit on a high-powered single machine. Great. We'll use Spark for this. It looks something like this, kind of like I showed you before. Our churned data is now tens of terabytes, and it looks like the code I showed you before. Great, we know how to do it. Easy, simple. I don't like talking about that one because I think you can see it in every other Spark talk. I think what maybe is a really interesting example that is slightly distinct from what I've described is distributed grid search. So in distributed grid search, again, it's the model training that's distributed. But we're not going to think about a huge input to a single model. We're going to think about having multiple models that we're training that are all pretty similar, but maybe have one hyperparameter that's a little bit different between them. And so it's the whole model training process that's distributed. So it's that image that I've shown you before, where what we're going to do is we're going to take 80% of it, train a model with a certain set of, oh boy, with a certain set of hyperparameters. And, oh, I was going to grab that in a second. Thank you. With a certain set of, thank you very much. With a certain set of hyperparameters. And, what was I saying? Certain set of hyperparameters. And then we're going to train a bunch of them with different hyperparameters. And so you can imagine that each node on our cluster is going to train a few of these models for us, and then we want to see which of these models actually perform best. And so the input data set isn't particularly large. We're just maybe shipping a copy of the input data set to each of the nodes. So we're going to, so we could do this with Spark, or we could do this with Scikit-Learn. With Scikit-Learn, there's no inherently distributed capabilities, but there's still parallelization, which means we can fit these models serially. So I try to find Swiss serial. I think I did an all right job. And the one that I think is the most impressive is Choco Crunch. So in Scikit-Learn, this is actually also incredibly easy, where what we need to do, given that we have this pipeline that we've specified, is to use this grid search CV function, which you can see that what we're trying to do is say, here's some parameters that we might want to change. So the number of estimators we're using in this, and I think this we're doing, yeah, gradient boosted classifier. So we have a depth for how many steps of gradient boosted we're doing. Might have 2 different loss functions we want to use. And the way that we make this parallel is we use this CV parameter. Yeah, I think the CV parameter will say, do cross-validation with 3 folds, and so you'll run 3 things simultaneously. So this is really, really useful. No, wait. No, the CV parameter doesn't do that. It's a different parameter. But you can see that what we want to do is change the loss function. And so this will train these both serially, so like one after another, using these 2 different loss functions. And then we'll fit it, and the result of that fit is going to inside of it, have a new attribute called best estimator. And best estimator will tell us for the output metric that we're evaluating our models on. So this could be area under the ROC curve. I believe it defaults to AU ROC. And it will tell us out of the different models that we've tried, which one's the best. So we're fitting these in order. But we may want to actually use the functionality that's built into Python to run things parallelly. So meaning these things will happen simultaneously in the same Python process, like asterisk, very weird things happen with the global interpreter lock, which is a Python-specific thing. So I used to have a slide about it, but I realized that it's too nitty-gritty and not worth it. But you can do multiple things at the same time as opposed to one after another. That's the short version. Here we have 3 different options for the number of estimators, 3 different options for the learning rate, and the 2 different options for the loss rate. And so, and I think 2 for max depth, and so on. So we have actually a huge number of different combinations of all these parameters that we want to try. And so we really do want to speed this up in some way. So we then say, I think this works, njobs, which says run 10 of these at the same time, essentially. And this can kind of work, asterisk, global interpreter lock, blah, blah, blah. There's fun videos and things to read about the global interpreter lock. But given enough combinations that you want to try, this might not be fast enough. You might actually have a very large grid, and it might take a very long time to train your models. And you might need it to finish training and give you your best model in less than a week, less than 3 days, less than a day, whatever your time limit is. So this is a situation where, there we go. This is a situation where it then becomes really useful to use Spark. I changed the slide and I didn't even notice, and that kind of drives home the point of this slide, which is to do this in Spark, there's now a package out called Spark_sklearn, where the thing that we've changed is the package that we're importing grid search CV from. So instead of from sklearn.gridsearch, we import it from Spark_sklearn. And we don't have that njobs anymore. It's just the same code that you used in Scikit-Learn before, and suddenly you can actually use this as driver code to execute your grid search on a Spark cluster. This, I think, is actually really, really powerful and useful, and fits very easily into normal machine learning workflows, and is something people should consider doing more of. Great. So 2 different ways for us to do distributed model training. And now I'm going to talk a bit about distributed model scoring. And drink this water. The first question to talk about when we're thinking about what it means to do distributed model scoring is, what do you mean by deploy? Often I will talk with people and they're like, oh, I want to put this model in production. And then I ask a few more questions about what it means to put something into production, and there's a huge variety of answers for what production means. Sometimes this is a SQL query that runs on a cron job. Sometimes it's standing up a REST server. Sometimes it's a nightly Spark job. So distributed model scoring depends a lot on what we mean by deploy. One very standard thing to do is to have a REST server available and to give your features or your input to this REST server and get some sort of response. We've seen a number of people today describe services that allow this REST interaction between your inputs and some sort of output. If you've serialized your model with PMML, the flip side of that is that you can then deserialize and serve your model with a variety of tools and systems. There's an open source tool called Open Scoring, which is a system that is literally has command line tools to stand up a REST server that then knows how to deploy and apply models. And you can see the REST endpoints that they supply here. There's companies that also do this. I believe there's one called Zementis, which is pretty popular. That's useful. It's interesting. But if you're doing distributed model scoring and not just sort of one-off in a production system, then you may run into some problems. So can you imagine taking a Spark cluster and before you start processing the inputs for a specific task that you're working on, you open up a client and you start just sending requests to this REST server. And each task that you're working on starts doing this. This is actually a really, really easy way to do a distributed denial of service attack on your own infrastructure. One of my favorite things about working in big data is that pretty much it's a lot of simultaneous distributed denial of service attacks that you're trying to prevent. And this is a classic example of people in a MapReduce job or in a Spark job opening up connections and starting to just completely overwhelm some single server. You can do something like put a load balancer in front of a bunch of different instances, but at that point you should maybe wonder if you're spending your time well. So another option in distributed batch model scoring, if you don't want to DDoS your own systems, is to do something like before you start processing a task in Spark, to make a POJO, a plain old Java object, or yeah, I actually am not sure how to deserialize PMML in Python. I don't think there's nothing that jumped out to me or has ever jumped out to me about that. And so I'm going to talk about this in Java. There's systems for creating normal Java objects that are models that know how to evaluate inputs from PMML files. And so this system is called JPMML. And JPMML is something that will create a plain old Java object from a PMML file, and then you can apply it to new data coming in. And you can create one of these inside your Spark workers and have it apply the model that you've created if you're doing something like running a Spark job on a cron sort of schedule. So my summary is that there are 3 ways that Spark can be used in workflows. One is training a single model on a huge amount of data. Another is training a ton of very similar models on some data. And then a third is applying a model that you've trained somewhere to many inputs. And the particular case that I talked about was PMML because it's pretty common. But hopefully I've also outlined some of the trade-offs of PMML. Thank you very much for listening to me, and I'm happy to take some questions.